Hi there, welcome back to video number 14 in our series on the calculus of variations. In this video we're going to look at some of what we did previously and also look ahead and kind of road map of where we're going to go in the next 3 or 4 videos. Now when we looked at our original problem, which was the hanging rope, then I said if we were to take a little section of the rope and shift it down, we would see a change in position and a change in gradient. So there would be position and gradient change. And what we did was we found a mathematical equation for these changes, and then we made them equal to 0, and we ended up with a Euler-Lagrange. So we had df partial f by partial y minus d by dx of partial f upon partial y derivative. And when we set these changes equal to 0, so in fact that looks like that one and that looks like that one, when we set these equal to 0, we knew we were in the equilibrium position. In this instance here, that would ensure that we had a extremum for the potential energy. Now the potential energy in this instance here is minimized, and now that's the process that we worked through previously. But it's not the whole story, because we don't just have position change and gradient change, we also have higher order changes as well. So you get a rate of change of gradient, which you could call the curvature. You also have a rate of change of the rate of change of gradient, and so on and so forth. Now what's the point in us looking further up here? So this one here would say, we'll just call that d representing the rate of change, and just call that dg representing the gradient. So that's the rate of change of the gradient. So what's the point in looking at this? Well, in this instance here, we know that if this function is, if this is equal to 0, then we will have an extremum, but it doesn't tell you whether you'll have a minimum or a maximum. Now a lot of the times, from the type of problem that you have and maybe even the geometry of the problem, you're able to tell whether you've got a maximum or a minimum, but you aren't always. So you could say that this test here is a necessary test to find out whether you have a local extremum, whether you have a maximum or a minimum, but it's not sufficient to tell you whether you actually do have a minimum or a maximum. You need another test for that, and that's what we're going to be looking at over the next few videos. Now it's directly analogous to the simple first order case. If we were to have a function and say it looked like that, and we know that the rate of change at the top here is 0, so that's just a function. Okay, so we know that f derivative of x, when f derivative of x equals 0, we know we would have a local extremum, but we wouldn't know from that whether it was a local maximum or a local minimum. We say that that there is a necessary condition for a local maximum, but it's not sufficient. It doesn't tell you whether you actually have a local maximum, because you could have, for example, you could have a minimum. That point there has got 0 rate of change, or you could have an inflection point in this direction, or you could have an inflection point in that direction there. Okay. So this is not enough to tell you whether you have a local maximum. Now there is another test that you can go through, which is if the second derivative is greater than 0, you have a local minimum. If the second derivative is less than 0, you have a local maximum. Okay, so looking at this, and this here would be your sufficient condition for a local maximum. So that's a necessary condition for a local maximum, and then that nails it, and that becomes your sufficient condition for a local maximum. Now it's directly analogous. We have a directly analogous issue in the calculus of variations, because we are not able to tell whether we have a local maximum or a local minimum. But if we look at this here, okay, this here is equivalent to a f double derivative. If we look at that second variation, and that one there would be a f derivative, and this here would be simply be our f. Okay, so this being 0 would ensure that we have an extremum, but if we were then to look here and we were to be able to tell whether we have a positive, this is positive, then if it was positive we would be able to say that we would have the extremum would be a minimum, and if it was negative we'd be able to say the extremum would be a maximum. Now what we're going to do over the next few videos is we're going to try and find a test that tells us whether our extremum is indeed a minimum or a maximum. And the kind of direction we're going to go with this, if I just get rid of this descaling out, give myself some space. Okay, now the direction we're going to go with this is that we have to try and figure out our function, okay, f double derivative. So we'll write these down. So we're looking for f double derivative, okay, so that's some function. We'll just call that function 1, okay. Now whenever we work out with this double derivative, this in effect is a total derivative, but it's the total derivative of the second variation, and when we work that out it's difficult to work out whether that is positive or negative. We have to simplify it in some way. Now the way we simplify it, and this is in effect the roadmap, is that we find out or we work out an equation for our, in effect, the Euler-Lagrange, but it's an Euler-Lagrange not for the first variation, but an Euler-Lagrange for the second variation. So we're looking for this function here, but a function like that which satisfies, or when we make it 0, ensures that the second variation goes to 0. Okay, so this here is produced from here, but we're looking for the same equation but for the second variation. Okay, now we derive that, and it's called, they give it a name, sometimes called the Jacobi accessory equation. So we call that, I'll just call it JAE. Okay, so we're looking for this JAE. Okay, I'll call that equation number 2. So we derive that. It's difficult to work with. So what we do is we derive this one here, and we use this equation number 2 to simplify this equation number 1. Okay, so that we end up with a very simple way of telling whether this here is positive or negative. Okay, so that's the roadmap, that's the route we're going to take, and it will take a few videos of a bit of maths in order to find the solution for this. Okay, thank you for listening and goodbye.